So, sorry, I got my internet bumped out there for a second for some reason. So, you guys can hear me now though, right?
Yeah.
Yep.
So did I disappear for a minute, or I don't know what happened. I
You got
looked up
kicked
and
off, or at least I did.
I kicked you off, yeah, but I think that my internet thing showed that I wasn't connected, and then I couldn't load this page, so I thought I'd just restart the whole thing. So hopefully it's all right now. Anyway, I'm recording, right? So, all right, so we're in okay shape. So anyway, there's a paper. So it's complicated. Let's see, what did I just do? Let me get it. Let me get a new window here. It's like I'm having a rough day today. For some reason. So the paper is this Parsi. So it's got, so the authors are like, there's some famous people here. Rubenstein is at North Carolina. He's a pretty famous simulation and modeling person. Grossberg.
Are you trying to share?
Yeah, I'm trying to share. Sorry about that. I'm sharing now though, right? Thanks.
Yeah.
All right. So anyway, Rubenstein's like pretty famous theory and simulation guy at North Carolina. Gary Gress at Sandia, he kind of invented the molecular dynamics simulation programs everybody uses. Grossberg actually interviewed at UC for physics, and they turned him down, and he went to Harvard, and now he's at NYU, I think. He does polymer physics stuff. And then who else is in this paper? Kurt Kramer's a famous German simulation guy, does also neutron scattering stuff. And so it's a group of people from different places. It's kind of interesting, right? So it's almost like an all-star team here on this paper. It's this year, and they're looking at ring polymers. Okay, so ring polymers originally, interest was in it because you had a thing. They're trying to do like the Rouse model for flow, which is an idea that you have basically if one unit of the chain moves, and it's going to affect its two neighbors, right? And then you add that up over all the chains, and you end up with the idea that the viscosity goes with the molecular weight. In other words, this is ends up being the train car thing. The more cars you add on, the higher the viscosity. Right. So you just make it one more like weight unit, then you get one more viscosity unit, 1-to-1 thing. But this, because you're dealing like with your unit and then the two pairs, then you come to the end of the chain. We'll talk about this in detail later on, but when you get to the end of the chain and you have that end unit, the terminal unit, then like it doesn't have that other pair. So you need what's called a closure. The closure relationship to get that thing to work, so you can calculate what the viscosity would be. And it's a complicated calculation. We'll talk about it later, but basically one way to get around that closure problem is to make it into a ring, and then there's no end, and then the next one, like I, goes to n. Like n would be the last unit, and then the next neighbor would be, so you have I plus 1, and then n and I, and then it's just a cycle, right? So that solves that closure problem. There's other ways to solve it, but that's one way. So cyclics became interesting to polymer physics people because of that. And then with DNA and RNA, a lot of times these molecules can come in a cyclic form. And those cyclic forms go through the transition where they make a double helix, and then the double helix kind of unfolds in parts to be read, right? So polymers, particularly ribonucleic acid or nucleic acids, DNA and RNA, can come in cyclic forms. So cyclics are interested there. And then polydimethyl siloxane, so silicon. Silicon always has a cyclic linear equilibrium going on. So your linear polymer chain of PDMS or whatever bathroom sealant you're using or it's also used for a lot of different things. Basically, bathtub sealant where you caulk around the edge is made of silicon, so that's a PDMS. And that's this Si with two methyl groups on it, and then oxygen is that polymer, right? So then it usually ends in OH, and this end ends in, but it's hydroxyl terminated, it's another OH here. That's usually how it is. These two hydroxyls can condense, and then it makes a ring with two end groups. So I mean, there's always a ring linear equilibria in PDMS. So some polymers that naturally occur in rings. So rings are of interest. And once people realized there was something to look at, then they put it into a rheometer. So a cone and plate rheometer. And then basically you get this behavior that the linear polymer has. So you see they both show power law fluid behavior. So it's a log viscosity, log shear rate. We'll talk about what a Wissenberg and a Deborah number are in a minute, but so you can see they both show this decay. There's a Newtonian plateau, so it's a Newtonian fluid at low shear rate. Then there's this time constant, 1 over the shear rate here gives a time constant for the relaxation of the chain. So that time constant has to do with under flow, the chain might stretch out, and then it takes time, some time constant for it to spring back to a random coil. Right, so some kind of relaxation time, tau. And that's associated with this tailover. Then once you get to this power law fluid part, the thing straightens out more and more. So it becomes more like a uncooked spaghetti that flows easily when you pour it out of the box versus cooked spaghetti with entanglements that doesn't flow at all. It doesn't flow much. Right, so the more you kind of stretch it with shear, it straightens out more. That's the cartoon. That's kind of this cartoon in a sense. Okay, so there's some kind of nuances to that are odd for rings. Okay, so and he doesn't, even though this paper is pretty long, and we're not exactly going to go through the entire thing, but basically, I mean, at this point, later on we could revisit this paper, but at this point we're not going to go through the whole thing. But basically, this is what their model is for this thing. Okay, that the rings kind of collapse down. So this is the shear flow. So this is a velocity gradient. He's arbitrarily picked a middle point where he sets it at 0 velocity, and then on one end it's got shear in one direction, the other direction is this kind of twisting force on the ring. He doesn't exactly explain why it collapses. So he just assumes that this is the structure. Okay, so in order for this to happen, there has to be a reason that it collapsed, but he doesn't mention that. So he just says this happens. Okay, so he has this 2 size scales that they're proposing in this thing. Okay, both of which especially the shear, both have been around, but both haven't really been used much. Right, so you have the coil size, that's the total size of the chain, right? And then you have this shear size. Okay, so the shear size is, right, so this, because, all right, let me go back to this plot. Where that plot is. Not that one, but this one. So these are for different molecular weights. The solid ones are linear. So this tailover points, this tau, which is indicated by the arrow here, right? So that's the arrow for the 84K linear, low molecular weight one. And this is the 185K or 185,000 grams per mole linear chain. And this is polystyrene. So that's a high molecular weight one, right? But this tailover point moves to different times. So the tau depends on the molecular weight, right? And so the molecular weight determines, so if that tau means the point where the thing relaxes to a coil, and if you're at a higher shear rate than that, it's straightened out, then there's kind of a in molecular weight, that's a size. So if you have a chain that's a random coil, the size is going to be the molecular weight times L squared. Right, so you have a molecular weight that has to do with this time constant. Under a certain shear rate, there's a certain molecular weight that corresponds to a certain size. And below that size, you have coils that are relaxed, and above that size, you have coils that are straightened out. right? So if you have a given chain, so you see this thing gets a little complicated. You have a given chain of molecular weight, big N, then it's going to be composed of these little things, these NS, the shear things that have relaxed. And then those are going to line up into this big N thing that's kind of straightened out. Right, so this squiggly S corresponds with NS. The squiggly S squared is NS times the step length squared, the Kuhn length squared. So that's what this eta S is. It's this relaxation thing. And one problem with this paper is that the two things are almost the same thing, right? So the difference is that this thing exists only in a dynamic experiment. In other words, under a flow, you get this thing develops. And when the flow stops, that thing disappears. Right. So this idea that, so because it's a time-dependent size scale, so it's going to depend on what this relaxation time is. So put another way, at any frequency, so I could pick any frequency here, that's a certain time. So there's a molecular weight where it would tail over there. And at that molecular weight, I could convert that molecular weight, that NS, to a size using this Gaussian function. Right, so I can say that there, at any given time scale, there's some molecular weight where it would tail over. That molecular weight is a size. That size is this eta S thing in this picture in figure 1. Right, so that's confusing. I mean, that's already confusing. This tensile size scale is another thing that's almost the same thing. Okay, this shear size scale relies on having a velocity gradient. So you have to be under dynamic measurement in order for that thing to exist. This tensile thing doesn't. So the tensile thing relies on that you apply a force to something that's coiled up like a telephone, like the old telephone handsets had a long, maybe you guys don't even know about that, but in the old days you had maybe seen in a movie. You'd have the headset and there'd be this coiled wire that went somewhere to a telephone somewhere that had a dial that you dialed, right? And you hung that up. I don't even know if that exists anymore. But anyway, these coils would tend to kink up. They'd end up being a mess like that. And if you pulled on it, you could see that it would straighten out. But locally it wouldn't straighten out. So globally it would. So you'd have your straightened out coil. You could do this with a string also. And then you'd have this length scale, which is the size of these things that aren't straightened out. And this is a different concept because this force that you're putting on is not a dynamic force, it's a static force. So in other words, you actually stretch the chain and then you end up with this size scale showing up, which is called the tensile blob size. So a blob, and this is called a shear blob in the paper. So blob means that you have a size scale. Below that size scale, you have one scaling. In both these cases, below that size scale, you have this Gaussian scaling. And in both cases, above that size scale, you have ballistic scaling, or linear. Right, so you have a transition, so you have this macromolecule, and then it has a transition size where the structure changes. Below it, it's random. Above it, it's stretched out. And both of these are the same kind of structure. In other words, you're going from a 2D, so df equals 2, to a 1D, df equals 1. So this means r goes with n. This thing means r squared goes with n. 2D, right? So that's the dimension of the structure. And the idea of this is that when you have nonlinear, non-Newtonian flow, it's always due to structure, right? So it's always, whenever you don't have a flat viscosity with shear rate, it's because the structure is changing. Something's happening to the structure. So that's a key point of this. So the rheologists all become structural people, right? Even though rheology has basically not much to do with structure. In other words, it's a conceptual jump from this to that. There's not a direct link that you can say this is due to a certain structure, but you need to have a model to say what's happening here, and the model is always a structural model. So verification of rheology models is going to involve some kind of technique like scattering, where you can measure the structure, or simulation where you can generate the structure. Right. So it's kind of important to see how this thing fits together. You're seeing a phenomenon where the rheology isn't Newtonian. It's not like water anymore, where you're not in Kansas. And then the only way that that can not be like water is if the structure of the thing changes due to the shear. And the model they have is this model of what happens when you shear it. In order to show that there's two different behaviors, there's a behavior for linear chains and behavior for rings that are different. So the slope here is 0.57 and the slope here is 0.89 between these two. So it's log. So you could draw a line of 0.9 up here and then 1 decade here, and you get the 0.89, which would be the linear one. And the 0.57 would be like half of this and one of these, which would give you the ring one. Right. So you can map out the decades, the power laws and these log plots that way, like with the decades. Anyway, so that said, so that's kind of what's going on. So this is their model. So what they do is they do an experiment. So they synthesize polystyrene that's in rings, and you do that by called a telecalic polymer. So you make a polystyrene, it's got like an A group on one end, a B on the other. And then you put under conditions where A and B react, and then they make cyclics. You could also make double the molecular weight, like B and then A. So you have to fractionate after you do this reaction. So first you make your polymer, you start with a B monomer, and then react with monomers, blah, 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 blah. And then you terminate with an A group. And then you take that polymer and change the acidity or something where A and B will react. And then you get either these rings that have molecular weight M, or you get these linear things that have molecular weight 2M. Then you do a fractionation to separate the linear from the rings, and you get pure rings that are monodisperse. So this is a kind of a standard technique. I don't think they do it in industry, but basically in the lab, people routinely do this thing. It's like a 3-step polymerization. And then they also simulate the thing, which isn't really exactly part of the. So that's where Grest comes in at Sandia. He's like a simulation person, so he simulates the same thing. So they have experimental data, they get the simulation data, they're the same thing. So that, and the point of that, I guess, is just to flex in their muscles that they could do it, because just the experimental would be good enough in this. But basically, they get the same behavior from simulation. He shows that somewhere here. Okay, down somewhere. This jointly data. This is the experiment and simulation data piled on top of each other. Okay, so he has this. So how do you get these? You have these different curves, right, for the rings and for the linears, and then you say, well, I have these relaxation times, right? So I know there's this time that the chain straightens out and then it goes back to coil. So I have this time, this 1/tau, that frequency. So I can normalize this frequency, this shear rate by that time, right? So I can multiply this tau by that gamma, and then I get the Wissenberg number. It's called the Wissenberg number. So WI, it's going to be that tau that I got there times the gamma. And if this thing is 1, then I'm at the gamma where the tailover happens. And if that thing's bigger than 1, then my chains are extending. If this number is less than 1, then the chains are in the Newtonian plateau. Right, so that way I can take this green curve and that blue curve, and I can make them fall on top of each other by plotting against the Wissenberg number instead of against the shear rate. So this is plotted against the Wissenberg number. So it's proportional to the rate of strain, but it's normalized by this relaxation time so that the solid curves all fall on top of each other, right? And then similarly, the viscosity, so the Newtonian viscosity changes. So we know that the plateau viscosity is going to be proportional molecular weight to the 3.4 in the entangled regime, right? So you take the viscosity, so you could see here that the viscosities are different at the plateau, but if you divide by the plateau viscosity, that brings those two up on top of each other, and then with the shift in the strain rate scale, that brings the curves to match, right? And that works. So that's good. That means you kind of have a rough idea what the governing parameters are. This tau and that plateau modulus, plateau viscosity are the two things that govern it, right? So that's good. That's nice. So that's one. So this is an experiment where. So in this experiment, what you did was you had your cone, you had your plate, you put your polymer in between. Again, this is 1 degree, so I've overemphasized it. And then I just turn it, right? I just let it turn. Right. So I'm not doing an oscillatory measurement, I'm just doing a constant shear measurement. And from that I get the viscosity, and I can turn it at different rates. So the shear rate is proportional to the angular velocity, and this and then the shear stress is proportional to the torque on that, right? So then I can get these measurements. It's a continuous shear measurement, steady viscosity measurement. So it's not oscillatory. So if you oscillate this thing and you do 1% strain, so you're at the low strain region, then you're going to get a different set of data, and generally that's interpreted in terms of the modulus. So you have like the stress by the strain is going to be this modulus. It's a dynamic modulus. You say you're going to fix a strain, and you have a time-dependent stress on it. Right, so your strain is going to be oscillatory strain, and then the stress, the torque that you get off it, is going to be offset by this del. Right, and from that you can get this complex modulus, which is going to have an in-phase part, and then it'll be, because you applied a strain that's a sine wave. And then it's going to be plus or minus this I G double prime cosine of what's going on. And so you have a storage and a loss modulus. The loss has to do with flow. This has to do with solid behavior. And when you plot that out, so this is a plot of that here. Let's see if I can get that bigger. Okay, so this is storage modulus and loss modulus, and it's plotted as a function of the frequency. Okay, frequencies here. And then it's plotted against frequency times a shift factor. The shift factor. So if you take a polymer at a low temperature, it becomes like glassy. Right? If you take it to a high temperature, it becomes like a fluid. In the same way, if you take it to low frequency, it becomes like a fluid, and high frequency, it becomes glassy. So basically, time and temperature are related to each other by an Arrhenius function. There's an activation energy over KT, and then you have like your time dependent, like viscosity. So you're going to have energy, activation energy, and then temperature. So viscosity is proportional to tau. So you have like time and temperature. So 1 over the frequency is going to give this exponential energy over KT. Then you can make this a little bit more complicated. You have the WLF function. Basically, this is good enough for most cases. Right? So you have a single parameter that relates time, frequency, and temperature. Right? So that this AT is that thing that relates frequency to temperature. So instead, because you can only measure over kind of 1 decade of frequency, if you measure it for temperatures, then you can get this AT and shift the curves to get a global curve for this. Right, and then these systems, so the solid of the linear chain. So we have G double prime is the loss part, that's the flow part, and then G prime has this power 2 here. In the flow regime, the low frequency. So if you go slow, it flows. So you have like liquid when you move it slowly, and then there's a crossover, then it becomes solid. right? And that crossover happens because the chains are entangled, and it's called the rubbery plateau because the chains link up together and make kind of a gel. Right, so you get this plateau, and if you take the that G prime at the plateau, we'll show later that that's proportional to KT over the molecular weight, or the entanglement molecular weight. So that plateau is a measure of the entanglement molecular weight for the chains. Right, so on this you can also take those same taus that you got from that viscosity plot, and it turns out that they happen at the crossover. This is called the crossover point. And there's two crossover points. There's one at low frequency where you get to the rubbery plateau. So below that, the chains can relax and they can flow. Above that, they become entangled. There's another crossover at high frequency where you see that chains, that these crosslink sites or these entanglement sites for a chain that's flowing through, like this chain's flowing through the entanglements, there's kind of a tube that it forms. And when you're within that tube, the chain actually flows in the direction of the tube. So you get, the chain can flow through that tube. That's called reptation. Right? And that happens at really high frequency. Right? So if you're over here, you see that the tube size has to do with this crossover here. Again, all the nonlinear features of this have to do with structure. So every feature you see in this that's different than a straight line is a structure. That's kind of the idea of this plot too. So this plot, the idea is this plot and that plot have the same information in them. And that's called the Cox Mertz Rule, right? Or Cox Mertz Law, that you can do from this oscillatory measurement. You can get all the same information you can get from the constant shear measurement. Okay, so you could, if you believe that, then you would take this frequency that you have here and multiply it by that same tau. Then these curves would become a universal curve also. Right? And also that Cox Mertz rule also means that you can calculate the viscosity from the modulus. So you can take this, so that means this oscillatory measurement's the way to go, because you have an unperturbed or low strain chain, and you can get ideal conditions. You can get this behavior on a much wider range of shear rate than you could get using a linear shear, because in the linear shear, weird things happen. So this is a third kind of experiment they're doing. So all these are done on the same machine. So it's the same cone and plate viscometer. So you either continuously turn it or you oscillate it at 1% oscillation. So it's vibrating, it's acoustic frequencies. And then the third thing is this part B. Okay, so in part B, you do put a constant stress on it. So you put a constant torque on this thing. Right, and then you look at the strain, kind of how this thing turns. So initially you put the torque on and it doesn't turn much, and then it kind of overcomes whatever's impeding it, and then it just goes to continuous flow. Okay, so if you think, so the modulus is the stress over the strain. So you're putting a constant stress on, so the torque is proportional to the stress. And this strain is proportional to the angular velocity, like how much it's moved. Angular velocity times time is going to be the strain. Right? So it starts out, it doesn't move very quickly, then it picks up speed as it turns. Okay, so that's called a stress. That's called a creep measurement. Okay, because you could equally say, if you had a piece of rubber or something that was gooey and thick, and then put a weight on it, and then you just watch it. This is a shear measurement, and this is a tensile. So you can do this in shear and tensile. If you do it in tensile, you just hang a weight on a gooey strip, and then it'll droop down. Right? And you can watch it just move, and as it moves faster and faster, the modulus drops. Right? So this is this creep measurement. So it's got initially So initially you got a plateau, and then you can see these taus, the same taus are marked, and this is time in this case, are marked in this curve. You can see the places where, so for the ring, it's where it tails over, where the modulus tails over. So similar to the viscosity measurement, you see a tail over, that's the relaxation time, the time it takes a chain to deform, right? And then the blue one for the blue, the low molecular weight, and the solid green for the linear. So the higher the molecular weight and the more linear, the longer time it takes for the thing to start turning. And once it starts turning, completely turning at a steady rate, that's just flow. So it's just flowing at that point, and the modulus goes to 0. Right, so all these measurements end up giving you the same information. They show this just because the machine does it, so they thought they'd show the comparison, and it's interesting that it works. Right, so the point is that all these dynamic features of polymers are all related to each other. They're all kind of the same thing. You can look at it from different ways, and it's all the same thing. And that's more or less what this Cox Mertz rule is. That you can do one measurement and get the same information as the other measurement. So you can get from this G prime, if you integrate the G prime, you can get the viscosity. So he says this viscosity, right? It's going to be G prime squared, G double prime squared, the square root, and then the divided by the frequency. So the viscosity times the frequency is a modulus. If you use this equation, you get the viscosity. You can plot that viscosity, normalize it by the 0 shear rate. Then you can put those curves on the same plot. So this plot has everything on it. It's got the G prime measurements. So the shear viscosity is the points, because you take fixed shear rates. This n star omega is this equation, G prime, G double prime. So the lines are the G prime, G double prime. And these are for the rings, the same thing. So the hollow points are for the rings. And then there's a fit to this curve. So these curves are fit. So these dashed best fits to crossover function use this function, which describes the shape of the viscosity curve. I think this is an empirical function. In other words, it doesn't have a theory. It's got a name though, and I don't remember its name. Maybe some of you guys know what it is, but 21 to 25. Oh, it's a Corot model. That's what it is. It's called the Corot model. And Yasuda model. These are like similar names. Armstrong wrote the book on polymer rheology. There's 3 authors, Armstrong, Bird, and Hossiger. Right? He was at Wisconsin, and then no, Armstrong's at MIT, and Bird and Hossiger at Wisconsin. So yeah, that's called the Corot model usually, and sometimes it's called the Corot-Yasuda model. But I think it's empirical. I'm not sure, but basically, from that you can fit these curves nicely, and you can get this slope, the power law slope, because sometimes it's hard to distinguish the power law regime from the tailover regime to the Newtonian plateau. So so that's that. That's a lot of what's in this paper. What else? So yeah, so there's a Wissenberg and the Deborah number. The reason we can put them on the same plot is because of this Cox Mertz rule. This has these 2 experiments on the same experiment, and then this is showing that the integral of this modulus is going to be the viscosity. So there's a lot in this paper. I mean, you won't get all of it, but basically, hopefully, you can answer the questions that are here. This part I more or less skipped, and then there's some kind of analysis at the end. So let me just go through what the questions are. Any comments on this thing at this point? Or so we got some time. So I say, so he calls these unconcatenated rings, right? So concatenated ring. There's also concatenated rings, which we might see later. So like the Olympic rings are concatenated, right? So they're, I forget how many, there's 5 or something, they're linked together. So if you pull on that, that's got a stress to it, right? And then these are unconcatenated, so they're supposedly like that, but they're in a melt, so there's a lot of them, right? So anyway, these are distinct features. This actually, if they're concatenated, they'll make a rubber. Actually, these can become like dynamic crosslink sites. So the Japanese are looking at this as new kinds of rubbers. There's quite a bit of research in concatenated rings. There's also this things about also that the chain, so chain wants to be random, right? So if you have a concatenation site, right, then this is stretched out here, so it wants to pull the ring that way. So you can make a molecular machine using this concatenation concept because of the entropy. So the randomness of the coils, there's a net force that shows up that wants to pull the thing that way. So you can turn concatenated rings into molecular machines if you want to. But anyway, so these are unconcatenated. That's why they emphasize that, because another topic. So in theory, like long rings originally are supposed to be the same thing as a long polymer. In other words, if you're using that as a closure for some kind of modeling, then you said that these two things are the same thing, right? And that, say up to like 1990, people were saying that. But then he's saying here that isn't the case. He says that actually, he said at the beginning, rings in the melt of longer rings adopt a compact state. That was, so this, if these two are true, then this is R squared is NL squared, and this is R squared is NL squared, the same thing. But if it's compact, it means that R cubed goes with N. So R squared goes with N to the 2/3 times L squared. That's 3D. Right, that's a collapse. That means this thing is actually a 3D object, like collapsed down. And normally, a transition is a collapsed transition between the expanded state and that collapsed state, which he doesn't talk about in this paper at all. Right, so there's something kind of missing in this paper, and that would involve thermodynamics, like temperature. Right, so he doesn't mention and some kind of interaction energy, so like the enthalpy of interaction. But so he doesn't mention that feature. He just says that long rings adopt a compact state with a gyration radius. This is just the size. Scaling is n to the 1/3, meaning it's 3D. Right? It's a function of the number of monomers, and compared to n to the 1/2, meaning 2D for linear chain. So Gaussian. So random Gaussian like the simulation, and this is something that's a collapsed 3D object, right? So there's some kind of issues with that, especially in the context of his model, the model that he shows here. So he's got this cartoon, and it doesn't look very collapsed at all, right? So his cartoon, the thing is a straight line. So he rectifies that by saying it collapses in this A to S direction, but doesn't collapse in the A to T direction. So, I mean, there's a lot of things in here that are a little strange, right? But basically, he can predict the slope of this. His point is to try to predict the slope of this viscosity curve, like this for the rings. Like, why does that go to 0.58, and why is it? He doesn't say why this is 0.89, but he says why that's 0.58 slope here. So, like in this plot. So let's see. So that's kind of that part. So both display shear thinning with different power laws. Then they approach the same value at the highest strain, which is kind of an interesting feature that he points out but doesn't really explain. So when you in this plot, like these things all lie in the same point out here. right? The linear and the rings all end up at the same place at really high shear rate. And that's kind of the experimental limit. If you go to a higher shear rate than that, the polymer will actually fracture in the middle. You can get melt fracture. So you can break the polymer fluid. And then you can also get slip at the walls of the plates. You have the cone in the plate. Right at the interface, it can slip, and it can also crack in the middle. So you can see if you put a tracer in it, you can see a straight line in the middle where you have melt failure. So polymers, you can break the fluid, you can crack the fluid, right? And that happens at high shear rate. So anyway, he shows that these collapse down, but he doesn't mention why that happens. But right. So anyway, figure two rheological measurements: oscillatory shear, creep. Creep involves application of fixed constant torque, and then at long times. That's just like explain the oscillatory shear experiment. You can Google that or whatever I said. You can parrot that back if you want. Then indicate where the polymer behaves as a fluid and where it behaves as an elastic solid. Okay, so that we went over in class. So we had that, like, in other words, it's fluid at low shear rate, where you get this power 2 and power 1. So the storage is going power 2, this is going power 1. It's liquid. The loss is bigger than the storage, that's liquid. Then becomes solid here because the storage is larger than the loss. Then it becomes liquid again out here when you get within the reptation tube, right? And then the plateau here has to do with rubber elasticity. So 1 over the molecular weight, kT by the molecular weight of between the entanglements that are causing this plateau. Because you're moving it so fast at that frequency, the entanglements can't relax. And then here they can relax. That's the relaxation time for the structure that forms. It's causing this plateau. There's another relaxation time here. So there's 2 taus in this. So the crossover frequencies are related to some time. Right? So that's kind of the idea of this plot. So the crossover frequencies correspond to these times, these relaxation times. And the arrows are like pointing to those. And then figure 4 is a plot with the shear viscosity, the strain to the Wissenberg number, blah, blah, blah. Comparisons made based on Cox Mertz verified and observed universal behavior. So this Wissenberg and Deborah numbers, they're the point where the system, in other words, when they're equal to 1, then the system's reached as at its relaxation time. If you're above it, you're applying too much shear and it can't relax. If you're below it, it can relax, right? So 1 is here, 10 to the 0 is 1, so that's your tau, right? That's where your shear rate or your frequency match the tau. That's all the action begins there, and below that is Newtonian. There's this kind of a cutoff point. So these two are ways to measure a comparison between the experimental speed that you're putting on the system and the natural speed of the system. In other words, how fast does it relax? And if you put too much on it, it can't relax, so you get this other behavior. So they're both ways to describe. One is for shear and one is for oscillatory frequency. That's the difference between them. Hopefully that's clear enough. And you can Google those too. I mean, there's a lot of things written on Wissenberg and Deborah numbers. Like, people are really excited about that topic. So you can find any number of things, Wikipedia or anything. I didn't look, but Wikipedia will have a long article on both those things, going through the history and the concept and things. It's a kind of a rich area for rheologists and other people. Like any kind of system will have this kind of response, like a natural relaxation time where it's unperturbed by whatever you're doing to it. So this is kind of when this is 1, you're at the perturbation limit of the system. Below that, it's an unperturbed whatever, and above that, it's a perturbed whatever. So you change in the structure and you get above that number. Let's see, figure 1 depicts a model used to explain the difference. So that's this cartoon. Actually, I could bring this up in the other, both of these at the same time. So like I said, it's a long paper, but it's just a few points about it to look at is what's here. And it isn't, the conclusions aren't that hard and fast in this paper. So it's more like a discussion in a sense of what's going on. And parts of it aren't that well answered, I guess. Let's see, there's a way to get both of these at the same time. I guess I'd click here. There. So, oops, that's not what I wanted to do. So figures 3-4 show that the alpha is 0.57 for rings and 0.85 for linear. And the model involves two size scales, the shear and tensile blob size. Blob is a subsection. So there's this definition of what is a blob. Right, so here, a blob is below that size scale, you have a certain structure, and above that, it's the same object. So below this blob size scale, you have one kind of structural scaling or one dimensionality or one fractal dimension, and above that, you have a different fractal dimension or some other behavior. Right, so the blob defines a transition point in structure, right, between kind of Gaussian behavior and then whatever happens at small scales. Right, so this thing, this small subsection of a larger chain, you can deal with as an independent molecule and apply your theory to it, right? And you can add those up on a larger scale to say what the entire object behaves. And that's kind of the point of this paper is he's breaking up the transverse behavior and the inflow behavior into two different behaviors, and he's kind of summing those together to get the total behavior that leads to the viscosity. And then he's predicting this power law 0.57 for the rings successfully. And he does that, and the 0.57 he gets from simulation and he gets from experiment. Explain the origin of these two size scales. So one is a dynamic size scale and the other one's a static size scale. He doesn't exactly say that, but you can read his description and use his if you want. Basically, this shear size scale, and you could also look up the papers that he references to talk about that stuff. Basically, the shear size scale has to do with under a shear flow at a certain frequency. It decides a certain molecular weight, and that's what this size scale is. So you'd say at a certain frequency. So there's a frequency for some, let's see. Yeah, so we could say we have like log viscosity, log 1 over tau, 1 over the relaxation time, which equals log of gamma, right? And then I have, this is the power law fluid. It's going to be for cyclic, it would be like the slope is negative 0.57, right? And then depending on the molecular weight, if I have a low molecular weight, this tailover would be here, and I have that tau. So there's a molecular weight, and I have that tau. Molecular weight 1, tau 1, molecular weight 2, tau 2. Right. So if I'm at this molecular weight, then I say the coil is unperturbed at that molecular weight, then I can say that molecular weight scales with r squared. Like L squared times that molecular weight is r squared, which is Gaussian. And this r squared is actually this eta s. So that equals eta s squared. Right. So if I can pick off the frequency in this curve, then get the molecular weight, then the molecular weight gives me that eta s. Right. So that's a little bit of a complicated number. Eta t, on the other hand, is just if you put a tensile force onto the chain, then the bigger the force, this eta t is proportional to kt over the force. So the bigger the force, the smaller the t, the smaller the eta t. That's called a tensile, and this is called a shear. And they're both blobs. Blob, the Gens, the French guy, came up with this word blobs. You can imagine a French person came up with this idea. It's not like a British or American scientific term, but anyway, that's that business. Then this is more philosophical down here. So I'm thinking that the latter questions are more for grad students and the earlier questions are more for undergrads, you know, so, but so he's saying, is this statement consistent with the cartoon? Not really, but then he explains it later in 2823 in the conclusions where he says the fractal nature and then computational blah, 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 retained compact fractal globule statistics in the Y direction. So it's transverse to the flow. He's saying it's collapsed, and in the direction of the flow, it's a rod. So that seems to be kind of a bogus explanation, but you can make it some judgment of that. And then also in that same region, he mentions something pretty interesting, that if you take this, so you have this shear thinning behavior, if you take these rings and put them into a tensile experiment, like you draw a fiber, so you put a force on it and do a tensile of the fluid, you find out that these rings have shear thickening compared to linear. Linear chains, no shear thickening. Shear thickening means this viscosity goes up. So that's what happens when you mix eggs. Think about mixing eggs and it gets more viscous as you mix it. So it usually means you're opening something up or making something more viscous as you mix it. His explanation for that is you get this, he's saying that you get these loops will somehow intertwine with each other and form a knot. So you can get a, he calls it a, some kind of a knot here. So that sounds like a pretty bogus explanation to me, but might just be me, but here, a cow hitch knot configuration. Okay, so this is something that somebody dreamed up that could happen. I think I know what a cow hitch knot is, but I'm not sure I can draw it. It's like you have two loops and they can intertwine with each other and form a knot, basically. So so whether that can actually happen, there's no evidence for it, right? So he talks about tumbling. So this shear thickening thing is something that's kind of interesting. I just wanted you to conjecture about it. Such behavior is not observed linear. So why does this shear thickening happening? Do you believe the cow hitch knot approach to it? This is just a philosophical question, or maybe you can come up with some answer for why this happens. So that's what the quiz is. We're kind of out of time. Any questions, anything on this thing? Or it's pretty difficult, but so I don't have high expectations for this quiz, or this homework, but just kind of do the best you can do. And I gave you till Tuesday, so we'll go over it on Wednesday next week. But if hopefully that's okay. And then, next week on Mondays, we'll meet in person on Monday, and whatever the classroom is. It's in Baldwin. Let's see, let me find that out. Baldwin 645. Right. So I'm going to try to record. I'm going to try to record the classes. I'm going to meet the guy today, to the UCIT person, to see about it. So anyway, let's quit there if there's no questions. Thanks.